All right, so welcome to the lectures on complex analysis. And here are the outline for this series. So the level of this difficulty will be pure math. And the text I'll be using is Serge Lang's complex analysis and also John B. Conway's functions of one complex variable. And you can find both of them online, free PDF. And the topics will be the complex field, the Euclidean space, the metric topology, power series, differentiation, integrations, and singularities. Okay, and a prereq for this complex analysis, we definitely need a single and multivariable calculus, and it's preferred if you know general topology. Okay, so the first lecture is on introductions. So we denote the set of all real numbers by R, and we assume a knowledge of the ordering of R, the definitions, the properties of primum, infimum, completeness, sequential convergence, and infinite series. For the field of complex numbers, we define it to be the set of all order pairs, where AB are real numbers, so C is basically same as R squared. I'll say it like this. And we define addition to be component-wise, and the multiplication is defined by this. So AB times CD will be AC minus BD, and the second component is BC plus AD. Okay. So if we put I is equal to 0, 1, the AB will be equal to A plus BI. And from this point on, we abandon the ordered pair notation of complex number. And by our rules of multiplication, we see that I squared is equal to negative 1. So that the equation z squared plus 1 equal to 0 has a root in C, right? And we can factorize this even more. So more generally, if z and w are complex numbers, we have this. Okay? If we just multiply out. And letting z and w to be real numbers with both a being non-zero, then we have this will equal to this. Right, because right, when we multiply a minus ib on the top and bottom, we get this, which can be simplified to this. So that we have the formula for reciprocal of a complex number. So with these definitions, it satisfies all the axioms of a field, where 0, 0 and 1, 0 are their identities for addition and multiplication, respectively. And yeah, they're additive and multiplicative inverses, right? So if we write z equals to a plus ib, we call a and b the real and imaginary parts of b, and we denote it by this symbol. So a is equal to rz, and b equals to iz. This is like a fancy looking I, okay? Iz. And if z is equal to x plus iy, we define the absolute value of z, or the norm of z, to be the square root of x squared plus y squared, to be the absolute value of z. And we define z bar as x minus iy to be the conjugate. So that we have this formula, and in particular, if z is non-zero, we have this formula. So all these content now, you might seen them before, right? And the following will not be proved are the basic properties of absolute values and conjugates, okay? So maybe you just pause and take a look at those. And right now we have our first theorem, is that for z, w are complex numbers, we have the triangle inequality. This is the triangle inequality. So how do you prove this? Let's just start with, because the absolute value itself is hard to work with, let's just work with the squares, right? So this will be z plus w times z plus w's conjugate, right? So this will be z plus w and z bar plus w bar. And you do the algebra, it will give you z squared plus 2. I'll write as re, okay, the real part. wz bar plus w squared, right? Now, we have this real part, we can estimate this. This real part, wz, is actually less than equal to the actual absolute value of this, right? Because the real part is less than equal to this. This is I think, yeah, you should be noticed, right? Thus, we can keep going, right? We can see this is z squared. We replace this with this when introduce inequality here, right? And w and z bar can even be separated. Z bar plus w bar. But notice that z bar and z has the same absolute value, so we're safe. And from here, it's just the formula for perfect square. Okay, so this is like the basic algebra of this proof. And the actual proof is here. Okay. 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 So the proof will be this will be equal to this, and we distribute this. So this gives you this, yada yada yada. And then because WZ bar is ZW bar bar. So if we have a complex number, we add it with the conjugates, it gives you 2 times the real part of it, right? And then we also have this is true, okay? Thus, we can introduce this inequality, which is equal to this, right? And we take the square root of both sides, right? We have this thing less than equal to this. Take a square root of both sides with, because this is our result. So by induction, we can have this is true, obviously, and we also have the useful inequality here that you should be noted, okay? And the polar form, well, for those of if you've done high school math, right? X plus iy equal to x will be r cos theta, y will be r sine theta. And the argument, we denote this theta as the argument of a complex number. And we introduce this abbreviation cis, means cos theta plus I sine theta. And we will multiply them, right? You're basically multiplying the magnitude and you're adding the angles, right? So we can written as this. And by induction, we multiply this, which is the multiple product of all the magnitudes and the sum of all the angles, right? So in particular, if they're all the same, will be Zn equal to Rn cis n theta, right? And also, this is also true, right? If Z is non-zero. So that this holds for all integers, positive, negative, and 0, if Z is non-zero. Okay, so here's a question. For a complex number that is non-zero and integer n greater than or equal to 2, okay, can you find Z satisfying Zn is equal to A? And how many Z that you can find? Right. And the answer is quite simple. This is also first year algebra. Right, it's called roots of unity. If you've done this before. Right. We just let, so if Z is this, we raise this power to the n. So this will be A and cis alpha, right? If A is equal to this, okay? If A is equal to this, right? So, and rotating by 2 pi, right? For any multiple of 2 pi, it also works. So this is called the nth roots of A, okay? So just to note this, okay? Is some recaps. And complex value functions is basically a function from a set of complex to the set of complex. The input is complex, the output is complex. So we have the real part and imaginary part of a complex number, right, where u and v are real numbers. And the real part, imaginary part, if we let z equal to x plus iy, right, x, y are real, so they are called like a multivariable function, right? So that's why we need multivariable calc here. It's just some notation introductions, okay? So here comes something that is more challenging here. We're gonna go through some knowledge of Rn. right? Because C and R2, they're topologically the same, so we give some essential results of limits in Rm. The norm we use this in C is the absolute value we use in C is actually the Euclidean norm in R2, right? So the results from Rm goes directly to C. So here, before that, I'll shout out to the Professor Stephen Yu, his notes for Math 247. I use his results in his proof and for this series, just for this part, okay? So the definition, we let an be a sequence of Rm. So each an, right, has m components, right, has m components. And for each index, right, the kth component has a sequence, right, because each component has a sequence, right? So the sequence and it is also determined, right? It determines and also determined by its component sequences, a and k, for each k. So the limits of component sequences. So given a sequence in Rm, okay? Now, the sequence is bounded if and only if it is bounded for all indices. So it is bounded if and only if each component sequence is bounded. And we have that if an converges to B, if and only if each component sequence converges to the component of B for all k, right? So if we assume this is true, right? If we have this is true, then we see that in complex case, if zk converges to a complex z, then the real part converges to the real part and the imaginary part converges to the imaginary part, right? Because we have 2, right? This is R2, right? The real part converges to the real part, imaginary part converges to the imaginary part. Because the norm we're using is actually the same Euclidean norm. So the proof of this, so there's a proof of this result. So first, let's just prove the first result. Suppose that, okay, why is this, looks like this? Okay, anyways. Suppose that an is bounded, right? So we can bound an for all n. But we have a and k for each k, the component, a and k. This is definitely true, right? So each component is also bounded. Suppose now that each component is bounded, right? Then we can choose rk for each k, right? We can choose rk for each k. Then we just take the sum of the rk's. We just take r as the sum of the rk's. Then by the triangle inequality, right? This is less than or equal to this. Right, this is the norm here we use is the Euclidean norm, okay? The norm we use in Rm is the Euclidean norm. Or sup norm or anything, right? If you took multivariable calc, you should be comfortable with this, right? And yeah, so the an is also bounded, right? So the sequence is bounded if and only if each component is bounded. And we talk about convergence now. Convergence. So to prove part 2, suppose that an converges to B, right? So we can choose the epsilon n thing. And this is, again, right? This is the absolute value, but this is the norm in R. So this always holds so that a and k converges to bk. Right? So a and k minus bk is the kth component of an minus b. Right? And suppose conversely, right, a and k converges bk. So we can do this estimation, right? And then we just take their sum, right? We just take their sum. Have at this. Then first we take the maximum n, and we by triangle inequality, right? This will be this, and it's less than epsilon, right? Because we have m copies of this. So A n converges to B, so this proves part 2. Okay, so yeah, we have the limits of component sequences. And operations of limits of sequences. Again, right, the sum of the limit is the limit of the sum is the sum of the limits, and it preserves the scalar product, and it also preserves with taking absolute value or taking norm, right? So it is actually just from the component convergence, right, of our theorem, right? Like for example, to prove part 1, the kth component of the limit, right? The limit of k component, right, is equal to this. And from here, we have the knowledge from R. The knowledge in R, right, implies that this is true, which is uk plus vk, which is u plus the kth component of u plus v. The rest is just as simple as it can be. Okay. And what we focus on is that the operations of limits of sequences in complex field. Okay. So if Zn converges to Z and Wn converges to W, then we have those. And this product is the product of complex numbers. And this is the division of complex numbers. And this is the absolute value of complex numbers. Okay. Well, to prove this actually follows from, okay, you know what, just let me just provide you guys the proof. The proof is that the first and last is just an application of R2, right? This is true. And for the third one, if we prove the third one, we prove the second one. So we just prove the third one, right? Do you agree with me? Right. So we just prove the third one, suffice. We write Zn as this and Wn as the sequence of Un plus Ivn, where xn, yn, un, vn are real numbers for all n. Right, just for clarity. Thus, if we multiply each z and wn, it will be equal to this, right? So if we write z equals to x plus iy, w equals to u plus iv, right? Then, like the limit, zn converges to z, right? So if we write z is equal to x plus iy, u is equal to u plus iv, right? Then we know that first we know that xn goes to x, yn goes to y, right? And the limit of x and un minus y and vn, because they're all sequences, this is all in R, right? So this holds in R and this also holds in R. Thus we have this converges to, this thing converges to this, and this thing converges to this, right? So now we have this is true, and then we have the component sequence thing, right? So this actually converges to this plus I times this, right? Zn times Wn. And this is precisely a Z times W, right? And for quotient, well, this, again, right, just by component sequence, argument, and R, right? Zn over Wn is a bit more complicated, but still can be simplified into this result. And notice the denominators, W is not 0, right? So they are not 0, right? So we can take the limit on n, where this converges to this converges to this, right? So combined gives this thing converges to this, right? Which is Z over W, right? Okay. And we're finally gonna move on to functions. If f is a function from AL to RM, RL to RM, where A is a limit point of A, okay, and B is an RM, then we say fx converges to B as x tends to A. We have this classic epsilon delta argument with our distance is just distance in Rm, right? And we have the sequential characterization of limits, right? The proof is similar as in first year calculus. And then we also have the component function, right? Like in Rm, we have the n components, just like what we did in for C, right? We have the real part and imaginary part. It's basically the first and second component, right? The kth component, so fk is equal to the composition of f with the projection map, right? And the limit of component functions, right? So the proof of it, right? So first read this statement. It's that b is equal to this. So fx converges to b if only if each fk converges to bk, right? So this is very similar as in, oh god, why is it like this? Okay. What did I do? Okay. Right, so first suppose that the limit fx converges to b, and for any fx, for any xn converges to a, then we have fxn converges to b, because this is true. So by sequential characterization of limits, we have this is true. And again, we have the limits of component sequences, right? We have this is true for all indices k. And secondly, conversely, right? Right. By this sequential characterization of limits again, right? Sequential characterization again, we have fkx converges to bk, right? X converges to a. So first of all, from this, we use the sequential characterization such that this holds for any limit, for any sequence xn. From here, we can go to the components, right? And for the components, we have this statement, so which we can apply the sequential characterization again. So this is true. And conversely, right, it's again the sequential characterization, limit of components, and sequential characterization again, right? And this gives the operation of limits on limits of functions, right? And Rm, so the proof is just follows by operations of limits of sequences together with the sequential characterization of limits. And so does the case of the complex cases, right? All we have here is just operations of limits of sequences and the sequential characterization of limits. And we're all in complex, right? So this is just some preparation or introduction of our thing that we're going to be using them in the future, okay? For f and g are all functions from complex to complex, okay? So the goal for this course is really just, for this lecture is really just show that the thing we did in reals, right? We have this in reals, the multiplication, the product, the quotient, the absolute value, they all remain valid if we're working with C. It also remains valid. And it just all flows from operations of limits of sequences in C and the sequential characterization of limits in C. Right. So yeah, we're done. See you guys next time.